Okay, so let's start the maximum likelihood estimation technique. The method of maximum likelihood estimation, which is known as MLE. Okay, so let's start with the aim. What is the aim of this estimation technique? So here we want to find the value of a true parameter that would most likely produce by the data that we in fact observed. Okay, so we are considering this likelihood concept and how likely some parameters will be produced by the observed sample. So this will be the main idea of this estimation technique actually. So to find the values of the true parameters so that would have the most likely produced by the data that we in fact observed. Okay, so this is the main aim, and for most cases basically these estimators have some optimal large sample properties. So we prefer to use MLEs because of this purpose. If you have large enough sample sizes, we know that they have good properties. For example, they have asymptotically normal distributions, so we can use normal theory when we are using MLEs. They are mostly consistent estimators, and they provide unique minimum variance unbiased estimators that we will see. They are not exactly the best estimators, but they are functions usually the best estimators. Okay, so let's first introduce the likelihood function concept. After that, you will understand why we need to maximize why we need to maximize the likelihood function. So you will understand that. I think then you will understand the main logic behind the maximum likelihood estimation technique. So we define the concept of a likelihood function first. Okay, so first we have a joint PDF of n random variables. There's f of x1 till xn with these unknown parameters, where theta is in the parameter space. We can have more than one parameter, theta represents the parameter vector basically. Be the PDF or the joint PDF of n random variables x1 to xn with sample values lowercase x's x sub n. Okay, then the likelihood function of the sample is given by this one actually. Likelihood function is actually a function of theta, where sample information is given to us. Okay, so it is a function of theta. So it is a likelihood of obtaining the certain theta given the sample values. Okay, so likelihood function is a function of theta. Okay, so it's not a function of x. So we assume that the sample information given to us, then how likely to obtain that specific theta is given by the likelihood function. Okay, but mathematically it is equivalent to the joint PDF of x values, but definition is totally different. In the joint distribution, what we are using, it's a function of sample values, sample random variables, given some specific theta value. So it is just the reverse actually. The meaning of joint PDF and likelihood function are totally different. Likelihood function is a function of a parameter. Joint PDF is a function of sample random variables given theta. Okay, so likelihood function is a function of theta given sample information, and it shows us how likely to obtain that specific theta given the sample values. Okay, but mathematically how we are finding it by using the joint PDFs, and usually we denote it by L theta. Okay, so we don't write x values most of the time. Okay, so it's a function of theta. So basically this part shows us the density or the probability of random variables given the value of theta. Okay, so for specific given value of theta, we can define the density function or probability function of random variables. So mathematically they are the same, but their meaning is totally different. Okay, so be careful about this difference. Okay, so then we can say that L is a function of theta for fixed sample values. Okay, how likely that obtained sample gives this theta value. So it is not a PDF or a joint PDF, but we are finding likelihood function using the joint PDF. Okay, and it measures, so this is important, it measures the support provided by the data for each possible value of the parameter. Okay, so for each different value of theta, we can calculate likelihood value, and then we can see which parameter value is most likely to obtain by using the sample information. Okay, so the basic logic of the maximum likelihood estimation is coming from the definition of likelihood function basically. For example, if you compare the likelihood of two parameters, compare the likelihood function at two different parameter points, like theta 1 and theta 2, let's say, points, and when we find that likelihood function at theta 1 is much more than the likelihood function for theta 2, so this means that basically the sample we actually observed is more likely to have occurred if theta equals to theta 1 compared to the theta equals to theta 2. Okay, so then we can say that the sample that we observed, that x actually, the sample we actually observed is more likely to have occurred if theta equals theta 1 than the case if theta equals theta 2. Okay, so also this can be interpreted as theta 1 is more plausible value for theta than theta 2 for the observed data. Okay, so likelihood that we observed theta 1 by specific data is more than theta 2. Let's consider another example to understand this likelihood concept better. What is more plausible, what is more likely to get case. Okay, so let's consider M&Ms. Sold in the USA and also sold in Canada. They have some differences. So we know that M&Ms sold in US have 50% red candies. Okay, and consider compared with the value compared to 30% that is produced or sold in Canada. In those sold in Canada. Okay, so there are differences in sold in US and Canada. In M&M sold in US have 50% red candies, and Canada it is 30%, the same thing. Okay, so let's say we want to do an experimental study. We have 2 bags of candies, let's say, or just 1 bag of candy, and then we want to see this bag or these bags are from Canada or United States, which is much likely, plausible to observe. Okay, so in an experimental study, let's say we get a sample of 5 candies. Were drawn from an unlabeled bag. We don't know if it is from United States or from Canada, and we get that we obtain 2 red candies were observed. Okay, is it more plausible, or the likelihood is more plausible that this bag was from the United States or from Canada? Okay, so we want to see that. Okay, so we know we have 2 red candies out of 5. So first of all, let's define our random variable. So out of 5 candies, we try to count the red ones. So which type of experiment we have? Okay, what is our random variable? Out of 5, we have fixed number of sample sizes. We randomly draw 5 of them, and then we want to search for the number of reds. So this is a binomial experiment, right? And our random variable x is the number of red candies among 5. Yazamadım. Among 5. So it's a binomial experiment. X distributed as binomial, where n is 5, and we have success probability p, and p is 0.5 for US, and it is 0.3 for Canada. Okay, so then what we observe, which is a lowercase x, is 2, right? So then after that, after observing my sample as 2, after getting the observed value, so then what is the likelihood that bag is from United States and from Canada? Then compare these likelihoods. Which one is higher? Then it is much more plausible to get from that country. Which one is more likely? Okay, so let's calculate the likelihood functions. Let's write the likelihood function. Okay, LP given X. Okay, so we have a binomial experiment. P choose X, 1 minus P to the 5 minus X. Then where X equals to 2, we have 5 choose 2, P squared, 1 minus P cube, which is 30 P squared, 1 minus P. Okay, so let's calculate this for United States and for Canada. So for Canada, P is 0.3 given 2. Okay, so when we calculate it, we get it as 0.03078. And when we calculate it for United States, we get it as 0.03125. The likelihood from United States is much more bigger, not much more bigger, slightly bigger than the other one, but this shows us that it is more plausible that the bag is used in the experiment was from the United States. So it is more likely, more plausible that the bag used in the experiment was from US. Okay. Okay, so let's consider the likelihood principle. So this is very important actually. This likelihood principle tells us about how the maximum likelihood estimators develop actually. So our estimation technique based on this likelihood principle. So let's say we have two sample points, X and Y. So these are two sample points such that, okay, so likelihood, we have a likelihood from the X and likelihood from Y, and these are proportional to each other, okay, for all parameter values theta in the parameter space. Okay, then the conclusions drawn from conclusions related to theta actually drawn from X and Y are equivalent or identical. Okay, so what this tells us basically from sample to sample, so when we get one sample we get different likelihood value, when we get another sample from the same population we can calculate likelihood in a different way. So if you want to estimate theta, okay, and the likelihood values for different sample points are proportional to each other, then this means that we get the same conclusion about the theta for different sample points actually. So when we get different samples, okay, so we will get same result about the estimation of theta. So this likelihood principle basically tells us this. So this means that the likelihood function can be used to compare the plausibility of various parameter values using different samples. Okay. Okay, so let's consider an example to understand this likelihood principle more easily. So consider the distribution, which is multinomial, where n is 6, and we have theta, and 1 minus 2 theta as parameters. So we have three values, x1, x2, x3 theta. So this is the PDF. 6 factorial over x1 factorial, x2 factorial, 6 minus x1 minus x2 factorial, and theta to the x1, theta to the x2, and we have 1 minus 2 theta, 6 minus x1 minus x2. Okay, and where x1 takes value x2 and x3 getting values 0 and 1. Okay, but they are bounded by 6, you know, when we get the sum. So the following two samples are drawn from from this likelihood. As following two samples drawn from this distribution have the same likelihood. Okay, so consider first sample as 1, 3, 2. So from here we get 6 factorial, 1 factorial, 3 factorial, 2 factorial, theta to the 1, theta to the 3, and we have 1 minus 2 theta squared. And let's consider we obtain this sample at the end. 6 factorial, 2 factorial, 2 factorial, 2 factorial, theta squared, 1 minus 2t squared. Okay, so basically when we get this form, only the constant part here is different. Okay, but we have theta to the 4 here. Again, we have theta to the 4 here. So these two likelihood values are actually proportional to each other, right? So this means that the information that I get from theta using this sample and this sample are equivalent. So I will get the same information in the estimation of theta if I get this sample or this sample. So nothing will change actually. Okay. So here we can say that both samples would lead us the same conclusion regarding the relative plausibility of different values of theta. Okay, so our aim is to be able to get some information related to theta for a given sample. So basically, if my theta is 0.5, okay, so then I can calculate this likelihood using this sample or this sample. And if you want to get theta as 0.3, let's say, and then again we can calculate the likelihood using these two. But the main point is my likelihood is much more bigger when theta is 0.5 than 0.3. So different samples will not affect my conclusion actually. Okay. So if I use this sample and then compare theta equals 0.5 or 0.3, then I can calculate the likelihoods and get which one is bigger, and do the same thing for this sample, and I will get exactly the same result related to this actually. This comparison, theta is 0.5 or 0.3, is much more plausible actually. Okay, so getting different sample points will not affect my conclusion regarding theta. Okay, let's see. Okay, so let me stop here. I will continue with more examples and then the likelihood concept. Then we will start how we can obtain the maximum likelihood estimators.